Hello. In this video we're going to be looking at Chapter 17, Lecture 16. We're going to be looking at KSP, molar solubility, mass solubility, and calculation of all of these things. So, when we were talking about an equilibrium, we can talk about equilibrium in terms of it being homogeneous or heterogeneous. With homogeneous, all the things are in the same state or same phase. But with our heterogeneous, we have things in different phases. So that's what we see in the in a solubility equilibrium. Okay, so our reactant in the case of a solubility equilibrium is a solid, and our products are aqueous, or in the aqueous phase. So that is what we're going to be looking at today, is solubility equilibrium. So here we're going to have a solid ionic compound dissolving into ions. Okay, so the reactant will be our undissolved ionic compound, and our product will be our dissolved ions. Okay. We have a special, or another, K that's associated with this. So it is an equilibrium process, so it has an equilibrium. So as equilibrium, so as such it has an equilibrium constant. And we call that constant the solubility product constant. Or KSP. Okay. And anytime we have a saturated solution, we use KSP. Okay. But generally, if we have a very soluble salt, we don't use it because we don't usually add enough solid in to get to the point where we're at our equilibrium. Okay, so an example of a solubility equilibrium would be something like barium sulfate. So according to solubility rules, barium sulfate is an insoluble compound. So it's considered insoluble according to solubility rules. However, nothing's truly insoluble. There'll be some amount of this that is going to dissolve. So in a saturated solution, we have the following equilibrium, where we have barium ions in solution and sulfate ions in solution, but mostly we are in the solid form. If we want to write the equilibrium expression for this, it'd be KSP, so the K for our solubility product is equal to our barium ion concentration times by our sulfate ion concentration. Okay, the barium sulfate in the solid phase would not be included. And what we can do with this is we can take it and we can take the saturated solution and dilute the saturated solution. So we can take a saturated solution of barium sulfate, dissolved, so be dissolved, and dilute it. So add in more water. So if we have, again, let's look at our equilibrium. If we have our equilibrium process, we add water in to this. It's going to decrease these concentrations. And as such, according to Le Chatelier's principle, we would form a reaction quotient. That reaction quotient would be less than K, so adding water. We get a Q that is less than K, so reaction quotient just like we've seen before. In order to reestablish equilibrium, we need to produce more ions. So if we dilute a system at equilibrium, a solubility system, so we go back to an unsaturated solution, if we have more solid left in, we will dissolve more of that solid. Okay, so if we dilute a heterogeneous system at equilibrium, we will shift towards the side with the greater moles of aqueous particles. Okay, now, solubility product, or KSP, and our solubility are not the same thing. The solubility product, or KSP, is the product of solubility, so multiplying, or the products of the soluble complex being multiplied together. So we can use our KSP and relate it back to solubility, but just keep in mind that we cannot say that our solubility and KSP are the same thing. Okay? So for solubility, we generally give it in terms of molar solubility, which is basically the maximum amount of moles of that solute that you can dissolve, or mass solubility, which would be the maximum amount of grams of that solute that you can dissolve in a given volume. We can take our molar solubility and determine our KSP, or vice versa. So if we have our mass solubility for a substance, we can convert it into molar solubility using our formula weight, and then using our empirical formula, we can determine our molar concentration of ions, and then those molar concentration of ions can go into our KSP expression. We generally try and, so for instance, if we have barium sulfate, breaking down into barium ions and sulfate ions, we can start it with some amount of barium sulfate, some solid, right? And we can dissolve a set amount, right? So this would be kind of like a rice table. So we dissolve some amount of that. So S is going to be amount dissolved. So amount of solid dissolved. So we dissolve that amount and we produce equal molar amounts of barium ions and sulfate ions. So at equilibrium, we don't really care about that, but we have S for our barium ions and S for our sulfate ions. So we would relate KSP and S, actually let's by putting in S in for our concentrations. So KSP would be equal to S times by S, so KSP in this particular case would be equal to S squared. So based on the stoichiometry of our compounds, we can determine our molar solubility using our KSP. So what I just showed you was if we have a compound where our number of ions, or formula unit, has one cation to one anion, we're going to call cation an A and anion B. And if we have one cation to one anion, we'd put S in for each of these substances because they are 1 to 1 as this dissolves. It'll go like that, so they're 1 to 1. So our KSP would be equal to S squared. If we have a ionic substance where we have A2B, then as it dissolves, it's going to produce 2 A ions and 1 B ion. So we put in 2S for our cation. We'd put in S for our anion, and then because A is squared, we would square the 2S. And what we get is KSP is equal to 2S squared times by S, which gives us 4S cubed. If we have AB2, then as our ionic AB2 dissolves, we produce 1 ion of A, 2 of B. So again, relating that solubility, we'd put a S in, 1 S in for A, 2 S's in for B, and because of this square, we would square this, and we get KSP is equal to S 2S squared, which again gives us 4S cubed. Next, if we have AB3, when that dissolves, we produce 1 A ion and 3 B ions. So we just put regular S in for our A, but we'd put in 3S in for B, and that would then be cubed, giving us KSP is equal to S 3S cubed. 3 cubed is 27, so this gives us 27S to the 4. And lastly, if we have a 3B2, when that dissolves, we produce 3 A ions and 2 B ions. So we'd have 3S cubed, 2S squared, giving us KSP is equal to 3S cubed, 2S squared, which would be 108 S to the 5. So this is kind of just a guide you can use to figure out how things dissolve and how you can relate that solubility to your KSP. Okay, so let's try this out. If we have magnesium fluoride with a KSP of 5.16 times 10 to the negative 11, we want to know what our molar solubility is. So magnesium fluoride, when it dissolves, produces magnesium ions and fluoride ions. Okay. Now, we could use the chart that we just made, realize that this is AB squared, and AB2 gives us 4S cubed is equal to KSP. But I'm going to go the long way this first time, just so I can prove to you that that is what that means. So, we're going to start out, again, with some amount of this. And as it dissolves, for every 1 mole of this, we produce 1 mole of this and 2 moles of this. So at equilibrium, again, we don't really care about that, we have S and 2S. We can then put that into our KSP expression. And we get KSP is equal to S 2S squared. So our KSP is equal to 4S cubed. We can then solve for S to determine our molar solubility. So 5.16 times 10 to the negative 11 is equal to 4S cubed. And if we do math, we get an S value equal to 2.35 times 10 to the negative 4 molar. So that S represents our solubility in terms of molarity. So this is the max amount of moles you can dissolve per liter of water. Let's try another example. If we have lead chloride, which has a KSP of 1.6 times 10 to the negative 2, we want to know what has a molar solubility of 1.6 times 10 to the negative 2, we want to determine what our KSP is. So, here we have lead chloride. When it dissolves, it produces lead ions and 2 chlorine ions. Whatever amount we start out with, when it dissolves, goes minus S, plus S, plus 2S. And when it dissolves at equilibrium, that S is equal to 1.6 times 10 to the negative 2. Right? So this is 1.6 times 10 to the negative 2, and this is 2 times 1.6 times 10 to the negative 2. Okay? We can then put that into our KSP expression. And we get a KSP equal to 1.6 times 10 to the negative 2, 2 times by 1.6 times 10 to the negative 2 squared, and we solve, we get a KSP value equal to 1.64 times 10 to the negative 5. Okay, that's it. See you guys later.